Right, so our next talk in room 3 is Kari Eifler from Texas A&M, and she will talk about quantum symmetries of quantum metric spaces.
Great, thank you. Yeah, so as Mike said, my name is Kari Eifler, and I'm now at Texas A&M. I guess you heard I used to be at Waterloo for my master's. So I'm completing my PhD here, working with Mike, and today I'll talk about quantum symmetries of quantum metric spaces. So there's really two things that I want to go over. Both of them are in my title. The first thing is quantum metric spaces. So I'll define what a Kuperberg-Weaver quantum metric space is. I'll hopefully give a lot of justification as to why they've defined it the way that they have. And then I'll talk about quantum symmetries. So we'll go over what classical symmetries are, talk a little bit about compact quantum groups, and then talk about the quantum isometry groups. So I'll start off with quantum metric spaces. I'm going to start off with the very easy classical case. So we're going to just take a finite metric space. Finite here means that the size of X is going to be finite. And of course, we all know what a metric looks like. That's going to be some D, which goes from X cross X into R. We know that these are the three axioms of a metric. It's just a quick reminder. But another way that we can look at these axioms is through this family of relations. So if we have these relations RT, this just says that X is related to Y if the distance between X and Y is less than or equal to T. Of course, we know equivalence relations. That's a relation where it has to be reflexive, symmetric, transitive. We no longer need those properties. We're just defining this relation like this. And we can see that these three axioms can now be recast as properties of this RT. So this first axiom, the distance from X to Y is 0 if and only if X is equal to Y. Well, this is the same as saying that R0 is the diagonal relation, or saying that R0 is just all tuples XX. The second says that the distance between X and Y is equal to the distance from Y to X. So of course, RT should be symmetric. We write this as just RT is equal to RT transpose. So if X is related to Y in RT, then Y is related to X in RT transpose. And finally, we have the triangle inequality. So this, we know what the triangle inequality is. How we would recast this in terms of the relations is that if X is related to Y inside of RS, and Y is related to Z inside of RT, then X is related to Z inside of RS plus T. And so we can just recast the axioms like this. And that's going to help justify the Kuperberg-Weaver quantum metric space definition. So they say that a quantum metric space on some von Neumann algebra, M, we can always put that inside of B of H, so let's do that. This is going to be a one-parameter family of weak star closed operator systems, VT. These are always going to sit inside of B of H, and we're doing this for positive T. And we want these three properties. So the first is that VT times VS is going to be contained in VS plus T. The second is that VT is equal to the intersection of all the VS's for S greater than T. And finally, we want V0 to be the commutant of M, or the commutant of that von Neumann algebra. So what this says, the rough intuition behind this, is it's saying that each VT is going to consist of the operators that don't displace any mass more than T units away from where it started. So it's restricted to that, and it's going to look something similar to these RTs, because we can recast these exactly like this. So R0 being the diagonal relation, this looks like the identity is inside of V0. Of course, because it's an operator system, it'll have the identity. And so that identity will be inside of V0. Again, the operator system says that it's going to be star closed, and VT is equal to VT star. And finally, this first condition, we can rewrite it here, where it looks exactly the same as these RS's. And yeah, once again, yeah, the rough intuition is that these VTs don't displace anything by more than T. Okay, so now I don't expect you to remember that definition, so I've put it at the top here. So these are the three properties of a quantum metric, and I'm going to start off by going through the classical case. So to see how this works in the classical case. Well, we're going to start off with the classical finite metric space, XD. And let's take the algebra M to be L infinity of X. This is going to be bounded multiplication operators on H. H is going to be L2 of X here. And we're going to give H the standard basis EX, where X is R in X. So this will be a finite basis. Just as a reminder what this means that for every F inside of the von Neumann algebra M, we can always embed L infinity of X into B of L2 of X. This is just going to act as that multiplication operator and MF, which acts in this way on L2 of X. And how we're going to define our VTs is as follows. So for any positive T, we're going to define VT to be all of our operators A in B of H such that the inner product of AEX along with inner producted with EX is going to equal 0 if the distance between X and Y is greater than T. So as soon as that distance is too big, you want A to send that, to treat this inner product like this. And another equivalent way that we can write this is we can say that it's the span of these rank 1 operators, BXY, they send G to the inner product of GY, EX, where the distance between X and Y is less than or equal to T. And so it'll be that span. And of course, I'm defining this a certain way, and it does exactly what we want it to do. So this is going to give us a quantum metric space in the case of Kuperberg-Weaver. So we can go through and see this really quick. So number 1 and number 2 are really easy to justify through this first definition. So we take all of our A's, and we can just go ahead and check those. For number 3, we can find that V0, that is going to end up being the diagonal here of just the VXX's. But VXX is the same as the multiplication operator on the indicator function just at X. And so because M is equal to the commutant of M, we end up getting that third property here. We can also go the other way. So conversely, if you have this operator M on L infinity of X for some finite set X, and if we know that this BT is a quantum metric on M in, again, the sense of Kuperberg-Weaver, well, then we can define this distance metric as follows. So the distance between X and Y is going to be defined as the infimum of the T such that there exists some A in V of T where this inner product is not 0. And this is going to end up being a metric on X. So you can see that there's this really good correspondence between quantum metrics and classical metrics, where of course quantum metrics generalize them. Okay. So now switching over a little bit, I'll start talking about quantum symmetries. So the symmetry of a structure X is viewed as the transformation of X, preserving all of its relevant properties. In the case of metric spaces, well, the only relevant property it has is the metric that it's endowed with. And so for a metric space, we're going to require that these transformations do not change the metric. And the word that we use for that is just isometries. The isometry group, or the symmetry group of a metric space, is how you could possibly think of it. This is going to be the set of all bijective isometries from X onto itself, and the group operation there is function composition. So of course, there's a number of natural properties that we get. They can be composed in an associative manner. There is going to be a trivial isometry, and each symmetry transformation is going to admit an inverse transformation, which is also going to be a symmetry. And so that's what classical symmetry is looking like. Well, now I'm going to switch a little bit over to compact quantum groups, and I'll define how we think of these. So I'm not going to be super rigorous here. I'll just give an overview of how we can think of them. So from Gelfand duality, we know that the theory of commutative C-star algebras captures all the information about compact Hausdorff spaces. So any commutative C-star algebra, that just looks like the function space of X, so C of X, for some compact Hausdorff space. Well, what if we want to look at non-commutative C-star algebras? We can say that non-commutative C-star algebras can be viewed as the function algebra of something called a quantum space, or C of X, where now we're generalizing that to quantum spaces. So also from Gelfand duality, we know that the structure of a compact group, G, so rather than just a compact Hausdorff space, we're now adding this group, or making it a group. This can be phrased entirely in terms of some extra structure on the commutative C-star algebra of functions C of G. And so in order to come up with a compact quantum group, rather than just a compact group, we're going to look at this same structure, so the same extra structure that we add here, but now for arbitrary unital C-star algebras. So it no longer has to be, it no longer has to be a commutative C-star algebra. And these were defined by Woronowicz in 1987, and they possess really powerful representation theory and are really interesting to us. But yeah. The name of the game is when we say quantum, what we really mean is non-commutative here, in some sense like this. You might have also seen compact quantum groups being this special class of Hopf algebras, but I'll just keep it as these are non-commutative analogs of groups. Okay. So one thing that we look at when we look at compact quantum groups is this magic unitary matrix. So a magic unitary matrix over some star algebra A, this is going to be an n by n matrix U, where each entry is inside of A, and it's going to be indexed, there we go, indexed by x and y with these two properties. So the first is that each entry is going to be a projection. So uxy equals uxy squared equals uxy star. And we also want the sum over every row and the sum over every column to equal 1. Because these are projections, this is also going to say that all of those projections in a single row are orthogonal, all the projections in a single column are also orthogonal. Now, let's look at the easiest case. So the easiest case is that we take this star algebra just to be the complex numbers. So if we do that, well then of course U is just going to be an n by n complex matrix. And this definition ends up being the exact same as a permutation matrix. So you can think of a magic unitary matrix as a quantum permutation matrix. Because it doesn't have this extra criteria, it can be now over any star algebra A. Okay, jumping around a little bit back to symmetries. So a symmetry group, Sn, is really important. And how we can define this, the function algebra on the symmetry group is by magic unitary matrices. So C of Sn, or the function algebra on Sn, this is going to be isomorphic to the universal C-star algebra, or the biggest C-star algebra, generated by the entries uxy, where if you put U to be uxy, this is going to be an n by n magic unitary matrix. And we also have this extra condition that the uxy commutes. And that describes the set, the function algebra of Sn, which we know and love and have studied quite a bit. Where, of course, Sn is going to be the symmetry group of a finite set with no extra structure. So there's nothing else said about it. You've just got n points, no extra structure there. And we can do the exact same thing by quantizing it. So we're going to define the compact quantum group, Sn plus, to be the universal C-star algebra, where we define the function algebra of Sn plus. This is now the C-star algebra generated by uxy, where U, defined in this way, is going to be a magic unitary matrix. So the only difference between these two is that we dropped this condition that the uxy commute. And Sn plus is going to be the quantum symmetry group now for a finite set with no extra structure. You can also define a co-multiplication on this set. I'm not going to do that, again, kind of sweeping the details under the rug, but if you're concerned about that, you can rest assured that there is a co-multiplication here. Okay, and so these are the two symmetry group and now quantum symmetry group for just a finite set with no extra structure. Well, from an operator algebra perspective, finite structures, like say just n points with no extra structure, they don't have very interesting symmetries, but they do have really interesting quantum symmetries. And this is true from this theorem by Wang back in 1998. So for n greater than or equal to 4, we have that the function algebra on Sn plus is not equal to the function algebra on Sn. So what this says is that C of Sn plus is non-commutative in this case. And the proof here is really easy. You just take any pair of projections, P and Q, inside of B of H, and we have that this matrix here is going to be a magic unitary. So each entry, of course, is a projection. You can check that. The sum over every row is going to be 1, and the sum over every column is also going to be 1. And so what this says is that even classical objects, say 4 points with no extra structure, they can have really interesting quantum symmetries that you don't end up seeing if you restrict down to classical groups. Okay. So now the next definition, I'm going to define the quantum isometry group for just a finite metric space. So we start off with our finite metric space, xd. Let's say that the size of x is equal to n. And I'm going to take this distance matrix D. So each entry is just the distance from the point x to y. We're indexing over all of our points, x and x. And how we're going to define the quantum isometry group, or remember, you can think of this as the quantum symmetry group of a metric space. This is just going to be, we're going to define it to be G plus of xd, and this is going to be the function algebra on the quantum symmetry group of n points. And we're going to quotient out by the ideal generated by the relations ud equals du. So formally, you can think of this as just adding extra isometric structure relative to the metric. Remember, in the classical case, U is a permutation matrix, and so we end up getting all isometries here. And so that is the quantum isometry group for a finite metric space. And our goal is that we want to capture this definition and expand it to now be defined for quantum metric spaces rather than just classical metric spaces. Okay, and so the way that we're going to do this is we're going to start off with a quantum metric space, let's call them VTs, on some von Neumann algebra M embedded in V of H. We're going to define GV to be the universal compact quantum group acting on H, which satisfies, the first is that we want there to be a fundamental unitary representation. U is going to be inside of V of H, tensor C of GV, or the function algebra on GV. Second is that by identifying H to be M as vector spaces, we are going to have for all T's, the conjugation action given by alpha U. It's going to map from V of H into V of H tensor C of GV, which just does exactly conjugation. So T gets mapped to U, T tensor 1, U star. We want this to leave VT invariant. So what that just says is that alpha U of VT is going to be contained inside of VT tensor C of GV. What this number 2 also corresponds to, so it corresponds in the classical case to saying that distances can't grow under the diagonal action of the automorphism group. Excuse me. So again, we want those not to grow by too much. The third criteria here is that at t equals 0, so remember when t equals 0, we have that v0 is equal to the commutant of m, then the restriction alpha u to the commutant of m, or just v0, this is going to then map into V0 tensor C of GV. We want this to be a quantum automorphism. And again, I'm not going to define what that is. I'll just say it's a non-commutative version of an automorphism. So this GV should really act by automorphisms on this quantum set. This third criteria says that, this third criteria in the classical case just says that U is a magic unitary matrix. So in the classical sense, it is a permutation or quantum permutation matrix. And so that's our new definition. And it's good because it does satisfy our goal. So if we take this classical finite metric space and we're letting M be L infinity of X, that's the algebra of bounded multiplication operators that act on H, or L2 of X, and we let these VT X be the standard construction of the Kuperberg-Weaver quantum metric as we did before, so just that span of those rank 1 operators. Well then, what we end up having is that Bonneka's quantum isometry group on a finite metric space is the same as our definition on this finite metric space. So it's good that it does work out. So I'll finish off with some motivation and some future work. So the first thing is the quantum information theory side. So when studying pseudo-telepathy quantum strategies for non-local games, what you end up naturally looking at is the quantum symmetries of graphs. And you can think of graphs as some sort of elementary example of a finite metric space. So for example, quantum automorphism groups of graphs, there's a lot of very interesting operator algebras that come up from these, and there's a lot of deep connections into quantum information theory. And it's natural then to ask, can you find a pseudo-telepathy game which have quantum metric spaces arising? The other thing is that these quantum metric spaces arise in many different guises. So they come up in finite spectral triples, Lipschitz semi-norms, but in the case of the Kuperberg-Weavers, we are able to extend it. Thank you. That's